It's our pleasure to be here and to share with you some concept and some new ideas about deep water deposits and reservoirs. As you know, we are a very small company aimed in providing high quality services to the oil industry. So, of course, everyone have problems with deep water deposit because this is a kind of environment that is very unfamiliar for us. But during these years, during more than 20 years, we had the opportunity to work for different oil companies in different countries and to see a lot of different environments in which clastic deposits accumulate. Many of those reservoirs and systems were related to deep water. So today we are going to move with this organization. We are going to start with some introduction of our objectives today. The idea today is, first of all, to outline the importance of turbidites as a mechanism for transferring sediments into the basin. As you know, going deeper and deeper looking for reservoir sometimes is challenging because our models are not always up to date. So we are not always update. So we are going to discuss with you some ideas about how the water sedimentation works. And so we are going to discuss some difference between two different kind of turbidites, intrabasinal and extrabasinal turbidite, a very interesting concept for understanding turbidites and related deep water reservoirs. So we are going to discuss also some new ideas about the link in between deltas and turbidites. In fact, in our vision of these days, extrabasinal turbidites we think are part of the distal part of deltas. We are going to discuss later on. And also we are going to introduce some new technologies we can apply to the understanding of the water reservoirs. I think we have a open, okay. So, I would like to start this speech with a definition of a very controversial concept. What is a turbidite? What is a turbidity current? Because in the papers, in the literature, there is a lot of confusion. For example, turbidity currents in origin is, some people have related turbidite currents and with turbulent flows. And I think this is a mistake because in the original definition, turbidity currents relate to turbid flows. So, what is in origin a turbidity current? In the original definition of Johnson in 1939, he introduced turbidity current for turbid flows that reshape the canyons. And according to this original definition, turbidity current referred to turbid flows, not turbulent. So all kind of flows that are turbid can be considered turbidites and turbidity currents. For example, cohesive debris flow, concentrated flow, hyperconcentrated flows, or sediment-laden turbulent flows for us are turbidity currents. So, and turbidity currents are not really related to turbulent flow condition. And another concept, for example, is turbidites are all those deposits accumulated by turbid current or sediment-laden density currents. This is the concept, the point of view of Professor Muti in the seminal book of 1992. And respect to the origin, turbidite can be intrabasinal or extrabasinal, as we're going to discuss much more in detail in the following chapters. So, intrabasinal turbidites. The concept of intrabasinal turbidites appears in the geological paradigm as a contrast with the energy barrier paradigm. As you know, during the 19th century, the geological thinking relate clastic material or quartz grainy deposit to littoral environment or continental environment. This is because, according to this paradigm, when the rivers transfer the sediment into the basin, quartz grain material will accumulate in shelfal or coastal areas, in littoral areas. So this is because, according to some oceanographic campaign, they take some sample from the sea floor, and they found that in the last 10 centimeters of the sea bottom, the sandstone content decreased as we move farther basinward. But it was an Italian geologist, Carlo Migliorini, who discovered the present concept of turbidites. For Migliorini, if we accumulate all classic sediments in littoral environment, this will result in gravity instability that tend to rectify this profile, and we are going to start this kind of flow, this turbidity current that is going to accumulate as a resedimentation deposit. So the original concept of the turbidite is that of the resedimentation. Conceptually, we can have different mechanisms of this gravity instability, but the most common is the gravity instability we can have in the slope, for example, and we can start this flow moving down the slope and generated this intrabasinal turbidity current. This typically intrabasinal turbidity current, you have many different flow transformation, and you can have, for example, a fast moving inertial flow and a slow moving turbulent flow. This is typically the B partition of turbidite. And at the end, when this granular flow stops, the turbulent cloud is going to pass over, so we are going to have the typical accumulation of graded beds. So for many geologists, the typical concept of the concept of turbidite is associated to the Bouma sequence. In fact, the Bouma sequence was very important for the sedimentology, for every geology, because give some prediction about the location in which we have in a turbidite system. So according to, as you know, Bouma recognized different intervals from A, B, C, D, E, going from graded massive bed, massive sandstone, then laminated ripples, and so on, with some silts. And basically, if you recognize the different kind of lithology and sedimentary structures, you can know in which position of the system you are. So this paper was fundamental for the understanding and the recognition of turbidites worldwide. More recently, Muti expand this concept of intrabasinal turbidite and also provide this beautiful track in which we can see how a flow evolved from a cohesive debris flow into a hyperconcentrated flow, then a concentrated flow, and finally a low density turbidite, go with different kind of phases. As you know, the transformation, along this transformation you have a lot of flow transformation, so this flow transformation results in different kind of deposit because the flow changes the way in which the sediment is supported inside and transferred inside the flow. So this is our typical deposit of intrabasinal turbidite, deposit of hyperconcentrated flows, deposit of concentrated flows, typical with dish structure, quartz grain deposit, and at the end, the BOMA sequence with these A to E intervals showing this normal grading. So this concept were very important for every geologist because provide some basic paradigm for the understanding of deep water deposit. So if we make a summary about the main concept of these turbidites, turbidites were originally related to re-sedimentation processes. Deposits accumulate at littoral shelf areas at the beginning and then were redeposited in deep water. This was the main concept of Professor Carlo Migliorini. And this resedimentation, very important, we need a slope. For this reason, for example, we don't have, and this according to this concept, shelf-fault turbidite, because for creating an intrabasinal turbidite, we need to accelerate the flow along a slope. So, and other important concept, if the accumulation is going to happen immediately after the base of slope. So you have a slope, you have a shelf, slope, the flow accelerates along the slope, and then we have these lobes, this accumulation of sandstone, typical turbidites at the end of slope areas. So if we go into a more recent and different concept, you know that in the year 2000, some oceanographers and geologists start to understand that turbidites can be triggered, can be supplied by directly a river in flood. This is very interesting because this turbidite is originated outside the basin, is extra basinal. And the characteristic of this kind of deposit related to this river in flood will be absolutely different respect to the turbidites you have associated to this setting, associated to the slope and base of slope. And as we are going to discuss later on, you have this paper. You can, if you have problem for download this paper, please ask me this paper. We can put this paper on the chat. And this is a paper in which we discuss the main characteristic and the main difference between intrabasinal and extrabasinal turbidites. So intrabasinal and extrabasinal turbidites, as you can see here, intrabasinal turbidites usually happen at the end of slope. You need a slope to accelerate the flow, and once the slope ends, you have these lobes. So you cannot go deeper because you are going to find mud here. But in contrast, extrabasinal turbidites are much more bigger because the main difference are these turbidites are supplied by a river, so you always have a delta, littoral deltas. Then you can have shelf-fault turbidites here, and at the end the location of these lobes and channels can be on the slope, at the end of slope, or also very deep in the basin. These flows can travel hundreds of thousands of kilometers far from the slope. So it's this kind of turbidites are very interesting, very important for understanding new opportunities in really deep water, exploration in deep water. So if we make a summary of the different kind of processes we have in deep water, you have turbidites, we have this turbidity currents, you have intrabasinal turbidity currents related to these sediment gravity flows. They are normally graded beds. You have intrabasinal components. This means that usually in this kind of turbidite you don't have extrabasinal elements like plant remains, like bones, for example, from mammals and any other extravaginal elements. In extravaginal turbidite, in contrast, are gravity flows, because gravity acts also in water and sediment in suspension that allow this flow to move basinward and to transfer the sediment very far in the basin. You can accumulate composite beds. Composite beds are not simple graded beds, but are beds that can change gradually in phases and lithology. So it's very difficult to try to understand this composite bed using the Bowman sequence, because if you take a core of an extravaginal turbidite, in some situations you can find 10 meters of massive sandstones that without any kind of sedimentary structure. So it is very difficult to understand this kind of deposit using the Bowman sequence. And the components, we can have together intravaginal and extravaginal components. This extravaginal turbidite can drag different components, different elements from the continent to the deep water. So it's very common to have in the same deposit a mixture of extravaginal components, like for example plant remains, and also find together some shell fall, slope, and deep water element. All these elements of the fossiliferous indicator together. So it's very confusing can be very confusing for a paleontologist, because you can explain the amount of extravaginal components. You have typical example in the Neuquén Basin in Argentina, which you take a sample in the Los Molles Formation, the Jurassic Los Molles Formation in deep water. In some samples you are going to find a complete dominance of extravaginal plant remains and pollen and all the stuff. So another interesting element you have here in extravaginal turbidite are lofting rhythmites. This kind of rhythmites are generated because of the reversal of the density, that is because of the freshwater content the flow has. This freshwater content is because we are dealing with a flow that was generated by a direct fluvial discharge. Another component you can have in this in deep water are all those kind of currents that can rework the sea bottom, and usually these currents are not really gravity flows or sediment gravity flows. This current usually make kind of sedimentary structures which are more similar respect to the sedimentary structure we can create in a flume, for example moving just water over loose sediment. So you are not going to accumulate massive sandstone or some typical deposits, as we are going to see later on, by this kind of bottom current. But they can be very important because they can increase the properties of this deposit as reservoirs, as hydrocarbon reservoirs. Okay, this is an example of how we can have together in the same deposit intravaginal and extravaginal deposits. For example, here you have deposit of concentrated flow, quartz granite sandstone with a lot of dish structures, and at the same time over a sharp surface you have this extravaginal turbidite with a lot of different grading. So you have massive laminated again in a single flow, also very large pieces of cold here and a lot of plant remains. This means that this turbidite had nothing to do with this lower bed related to intravaginal turbidite, and this one relating to extravaginal flow. So what's the important for this? Here we have another paper you can download. in which we discuss the different kind of deltas and the different kind of flows that can generate from littoral deltas, from Gilbert delta, or from subaqueous delta. This is the classification of Bates, and surprisingly, Bates proposed this classification more than 70 years ago, because this classification was proposed in 1953. So Bates believed that the kind of delta we can have, it will depend on the density of the incoming flow and the contrast in density. So if you have fresh water enter in marine water, so this will create will force all the sediment to accumulate here and form some kind of moss bar, and with the delta front and prodelta deposits, and the silt and clay will form this plume from which the sediments will collapse, forming the prodelta. This is another particular situation in which the density of the incoming flow is similar to the density of the water in the basin. So the typical situation of freshwater lakes, in which a river enters in a freshwater lake. In this case, all the sediment transported by the river collapse, and you are going to have this kind of steep slope deltas or Gilbert deltas. And finally, this situation happened when the river discharged a mixture of water and density with a bulk density which is higher than the density of the water in the reservoir. This is very interesting because it can happen also in marine basins. So the river discharges a lot of sediment, and these sediments are not going to stop at littoral area, but are going to move basinward and transport the sediment very far to the inner basin, also very far from the slope. Here you have this effect of downwelling. This downwelling is very important because light material like plant remains, roots, and pieces of wood cannot buoy here, forming this buoyant plume, but will be dragged together with the flow and can be transferred directly very far inside the basin. So what are these hyperpignal flow? This is a video, and you can put it here. Okay, this is a video of a present hyperpignal flow in marine setting. So these hyperpignal flows form from rivers in flood when in the marine setting, when the river discharges a mixture of water and sediment with a density that is higher than 35 kilograms per cubic meter. So as you are going to see, this density can be much more higher. So depending on the characteristic of the sediment law, these sustained hyperpignal flows can be pebbly, sandy, or muddy. And these flows are very different with respect to those associated to intrabasinal turbidite, because they have a slow moving head with a low entrainment of ambient water. So these flows can transfer not only extrabasinal component, but also can transfer fresh water very far into the basin. And this in many reservoirs, some geologists found a lower salinity in the original water in the reservoir in marine setting. This is also an indication of a hyperpignal origin of these deposits. So going back into some examples, this is the Florida Scarmen in the Gulf of Mexico. As you can see here, you have the two kind of turbidites together. You have this along the slope, you have these gullies, which in fact are intrabasinal turbidite. Along the slope and at the end of slope, you have these lobes. And on the other side, at the end, at the bottom of the Gulf of Mexico, you have these beautiful meanders here. And these meanders are related to extravaginal turbidites. Extravaginal turbidites have channels and lobes, and in some situation can resemble a fluvial system. So this is a cartoon showing how hyperpygnal flows are very sensitive to the topography you can have in the basin. For example, if you have mud disappears, you have falls, or you have some relief in the basin, this kind of flows can try and go into to flow and to travel, trying to find the lower landscape you have in the basin. So this situation creates very important opportunities for exploration, because you can have very thick succession of clastic sediments related to this hyperpygnal flow. And also very important, hyperpygnal flow can travel also in very low slopes. So very usually also in horizontal settings, hyperpygnal flow can travel and can find the lower landscape areas to accumulate the sediment. This is another paper you can download. This is a more recent paper about a new classification of deltas, in which we relate, on one side we have the density of the mixture of water and sediment provided by the rivers. So you have clean rivers here for sediment-free rivers. Then you have dirty rivers, increasing the concentration. As you can see, this is a logarithmic scale. So this is the concentration of kilogram for cubic meter of sediments. And on the other side, you have also in logarithmic scale, you have the density of the water. So you can go from fresh water, brackish water, and marine water, and also saline water. In the middle, you have this threshold. This threshold is the homopygnal threshold, in which the density of the flow and the water in the basin is the same. So you have different fields here. For understanding extravaginal turbidite is very important, this field in which the density of the flow is much more higher than the density of the water of the reservoir. And in this field we are going to create some channels and lobes that can accumulate the sediment on the shelf and also on deep water. So in this, according to this point of view, this kind of extravaginal turbidites are in fact a part of a very big delta system. Deltas can work at different levels of efficiency. You have these littoral, marine littoral deltas, when the river discharge, especially just water with a low content of suspended load. Then you can have these hyperpygnal littoral deltas that create these beautiful parasequences on the shelf, in which hyperpygnal flow interacts with waves and tides. And at the end, if the fluvial discharge is concentrated enough, you can transport these sediments into the or also into deep water through the canyon, and you can create this very big, very thick succession of lobes, very important for reservoir, for hosting hydrocarbons in deep water settings. It's very interesting if we compare intravaginal turbidite with extravaginal turbidite. It's very important because extravaginal turbidite don't depend on the slope, because the rivers are continuously pump the flow. So also if you have in a horizontal bottom, basin bottom, also this flow can continue to travel. So we don't need a slope to form and to travel far. hyperpygnal flow can travel long distance also in near flat settings, and the thickness of the deposits associated to hyperpygnal flows will be very sensitive to the subaqueous topography. So if your basin bottom is not absolutely sharp, like in the Gulf of Mexico or in the offshore of Brazil, when you have a lot of salt diapirs or mud diapirs, you can have a lot of opportunities associated to this topography, because hyperpygnal flows can create very interesting accumulation also on slope settings, on deep water settings. And last phases, the phases you have in these extravaginal turbidites, as we are going to see, are very different respect to the phases we have in intravaginal turbidite, respect to the Bowma sequence. For example, if you go into a deposit, this is an example from the Trinidad Tobago, Mayaro Formation in the cliff of East Trinidad. If we compare the kind of deposit we found here, this is, for example, a massive sandstone with some interbedded of laminated sandstone. This is a single bed. It's a bed related to a single deposit. If we try to understand this deposit using the Bowma sequence, of course we are going to have problems, because we are not going to have this normal grading and this normal succession of sedimentary structures. We can have very, very different deposit, and this is especially related to the dynamic of these flows. These flows can last for several days or even weeks or months. So along the fluvial discharge, the properties of the flow can change. So the deposit is going to show internally the variations, here variations in grain size, in sedimentary structures, making this composite bed. Also the flow can accelerate and erode the basal part of the flow. And very interesting, you can have also bedload deposit, because the overpassing turbulent flow can provide some shear at the bottom, and at the end, when the mixture of water and sediment becomes much more lighter, the flow can revert the density, and you can have this buoyant plume that create the accumulation of these lofting deposits. So basically the kind of phases we are going to have in this associated to these hyperpygnal flows are simple, because you have bedload deposit that resemble those phases you have in rivers, and because you have bedload and all the kind of thing. Usually the main difference is the amount of sandy matrix you have in this conglomerate. Also you can have suspended load deposit related to the collapse of the sediments transported in suspension inside the turbulent flow, and at the end we have these phases related to lofting that result from the density reversal provided by the fresh water. So these phases B, S, and L are three families. We are not going to go deeper during this presentation about the kind of phases you are going to have in detail, but these families of bedload phases, you can have massive gravels, cross-bedded sandstones, quartz-graded sandstone with gravel asymptotic cross-bedding. Also this quartz-graded sandstone with aligned pebbles. You can have the equivalent of this deposit also with clay chips, very common. And when this turbulent flow collapse, then you can have massive sandstone, laminated sandstone with gleaming ripples, and also in shallow water you can have this shellfish shelf-fault turbidite or shelf-fault sandstone slopes, as Professor Muti called. In this case, you have sandstone with hammocky cross stratification, with wave bedding, and so on. So it's very also interesting that you can see this transition in a lateral position. If you go from the central part of the flow toward the lateral, you can see the how the flow decrease the energy and the velocity, and you go from conglomerate, massive sandstone, ripples, and finally you have the lofting plumes at the lateral at the levee. It's very interesting because at the same time you can have erosion in the channel and deposition on the levee through this lofting rhythmite with a lot of plant remains, micas, and all the stuff, laminated deposit. So a typical deposit of an extravaginal turbidite current, the composite bed, in which you have changes, gradual changes between gravels, massive sandstones, gravels again, laminated. This is the vertical, an example of the vertical succession, and you can see how the original flow fluctuates and the results in terms of lithology and in terms of sedimentary structures. To understand better how we can create this poorly sorted sediment, this is for many sedimentologists, for example, for Professor Shamugan called this sandy debris flow or sandy debris because according to Shamugan, it's very difficult to explain how we can have this floating crust here inside sandstones, because according to his concept, if we have quartz grain material, should be at the bottom and not on the middle. But this is because of a process that is called hindered settling, in which you have a turbulent suspension that drags the sediments at the bottom, but at the same time you have the accumulation of part of the turbulent suspension. So you can have together a bed load and suspended load. So for this reason, I would like to share with you, to discuss with you an experiment in which you have a turbulent flow here. It is suspended load that at the bottom transfer bed load. As you can see here, this bed load is trapped inside the suspended load. So you are going to see some floating crust here, and at the same time the bottom of the deposit is rising. So this is at the same time deposits and the bottom of the flow. So if the flow continues with the time, you can accumulate a very thick succession because it depends on the time. It's not just it's like you are recording all the fluctuation in flow velocity and flow competence and flow capacity along the flow. This is very small because it's very difficult to create this kind of experiments in flumes. But in natural environment, you can accumulate single beds very thick, in some situation more than 40 meters thick for single beds. Another typical characteristic of extravaginal turbidites of this deposit of hyperpignal flows is when you have in this massive sandstone a lot of extravaginal components. For example, these are charcoal pieces probably related to wildfire, and also you have here some leaves, very big leaves, and also pieces of leaves. You can have trunks, pieces of wood, all kind of things together with marine elements, also deep water elements. And another point of very interesting is to understand how massive sandstone form, because massive sandstones are very important for deep water reservoirs, as we are going to discuss shortly. So this is some flume experiments. Some geologists create this device more recently to try to accumulate or try to create massive sandstone. Because if you move just water over sandstone, you can create ripples, you can create cross bedding, you can create planar lamination, but you never will be able to create massive sandstone. Massive sandstone, in fact, are the result of the collapse of a turbulent suspension that results in the bottom in a laminar flow. This is a gravity transformation in the sense of Fisher 1983, and this gravity transformation, you can see here, you don't have a sharp boundary between the flow and the bottom, so all is gradual, so you cannot create sedimentary structures in this context. And you can see the gradual change in velocity. The direct evidence is the flasher bedding. This is because velocity changed from bottom to the upper part, and you can this deflection. So this is indirect evidence of we are dealing with. This is another video. Mariano, start. This is very interesting flume experiment, because we can see how a mixture of water and sediment in a flume experiment. Initially, we are going to have a turbulent flow, and this turbulent flow is going to collapse. The sediment in the turbulent flow is going to collapse, and at the bottom, this flow is going to transform to get a flow transformation from a turbulent flow on top into a laminar flow on the bottom. So you are going to see a sharp boundary. As you can see here, the main composition of this flow is more than 50% is very fine-grained sandstone. So in the film, the first experiment, you are going to see in real velocity, so the turbulent flow, and at the bottom you can see here this sharp boundary in which you have this laminar flow in the bottom. So massive sandstones accumulate in this context, so no possibility to create ripples or create another kind of sedimentary structure. So this is a low velocity, this is a turbulent flow, and the flow transformation start to happen when the sediment collapse, and you are going to see in some moment here some sharp boundary here, sharp boundary between turbulent flow here and laminar flow condition in the lower part. The laminar flow, the velocity decrease from the top to the bottom, and the accumulation here is gradual, so no chances to make ripples or to make any other sedimentary structures. So this is a cartoon made by Mariano showing how the accumulation of massive sandstone is gradual, and this change in velocity in the laminar flow and together with the deformation of the shale create these flumes that suggest the direction of the flow. So this is for the origin of this flame structures. Okay, why these massive sandstones are important? Massive sandstones, the original packing of massive sandstones is very loose. Originally, the porosity can be very high, near 50%. And of course, this is because the laminar condition at the bottom of the flow that cannot cannot organize very well the sediment. So according to the flow capacity, the maximum size of the sandstone is limited, but not the finite material. This makes massive sandstone very sensitive to the kind of material you can have in the matrix, because you can have some diagenesis or some diagenetic problems in the future. And also it's very interesting because also these massive sandstones are very sensitive to compaction. So if you migrate oil into massive sandstone very early in the deposition, probably you can preserve some very high porosity condition. But if you try to migrate oil in a sandstone, a massive sandstone that was buried very deep, probably you are going to have a lot of problems because the porosity and permeability will be reduced very hard. And another characteristic of these massive sandstones, they usually contain a lot of plant remains because these leaves, for example, are contained inside the flow, and as the flow collapses here, you can see these leaves can be trapped inside massive sandstone. This is an example from the southern part of Argentina, Ushuaia, for deep basin. And another characteristic of this extrabasinal turbidite is, in some situations you can have massive sandstone, and on top of massive sandstone just lofting deposit. So the sequence is not like the Bouma sequence, because in some it's very common that the flow revert the density at a velocity higher respect to the velocity, necessary velocity to create ripples. So in this case you don't have ripples, just massive sandstone with some lamination here, some diffuse lamination, and then lofting deposit with a lot of plant remains. This is another kind of phases typically and very distinctive of these extrabasinal turbidites. And finally, you have to take care about the kind of bodies you can accumulate according to this extrabasinal turbidite, because it's very common to have these shallow channels, but these channels at the same time has this kind of levees, and at the end the final accumulation is a mixture between a channel and a lobe, and can create some kind of topography in the bottom. We found this problem in Trinidad. For example, we create this model to try to explain what kind of distribution of somebody we have here, and how we can solve and how we can understand the problems of connectivity. So as the flow and the deposit create this kind of topography in the bottom, they constrain the accumulation of the forthcoming flows and deposits. So as you can see here, the stacking can be very complicated, and you can see this kind of logs. For example, the correlation can be difficult. You have to understand that to try to get a better correlation. Finally, okay, this is a summary of the problem we have in the fossiliferous content of extrabasinal turbidite. Usually you can have a mixture of different components. Recently we published a paper in which we found in Vaca deposits of deep water in the Vaca Muerta formation, more than 300 kilometers far from the coast, we found elements of brackish and shallow water environment, probably eroded from very shallow position and transferred into the basin, but by muddy hyperpignal flows. So what about the models we have for exploration? The models we have in the literature for understanding turbidites are very limited, because all these models were created in active margin. For example, Southern Apennines, California, Pyrenean fault belt. So all these models are basically applied for intrabasinal turbidite. You have the slope, and then you have the this kind of lobes. So we have to take care, because if you are exploring in passive margins, like offshore Brazil, like in Gulf of Mexico, probably you are going to have a lot of extrabasinal turbidites, and the models associated to extrabasinal turbidites are absolutely different respect to the model of this kind of intrabasinal turbidite created from this for these collisional environments like those we have in the in the main outcrops of Europe. So extrabasinal turbidites are essentially deep water deltas. So these slow fan models are not necessarily valid for this kind of system, because also we can have this extrabasinal turbidite also on the shelf. This is a cartoon showing the different kind of deltas, and in this context you can have these fan deltas, littoral deltas, marine littoral deltas, hyperpignal littoral deltas, subaqueous deltas. You can have subaqueous deltas on the shelf, you can have subaqueous deltas on the slope, and you can have subaqueous delta in the deeper part of the basin. And also these deltas can extend very far from the slope, because we don't need a very high gradient like you need in the slope here for intrabasinal turbidite. For example, these mass transport complex are typically an example of intrabasinal turbidite. So before going to same case study about deep water reservoirs, I would like to share with you some new technologies we apply to understanding of deep water deposit. Of course, we can apply this technology for every kind of deposit. We also work in carbonates and any other kind of deposit, and especially we use AI. AI is very important, and we work with two different branches of AI, as you know, computer vision and machine learning. Machine learning is important because allow you to propagate a sedimentological study you can make using a core in some specific position of the basin, and then you can spread out all this model and understand better in wells that don't have cores, just you have just logs. And computer vision is a very important tool because will allow you to take all information, all possible information from core, from tomography, and also from images, well images, borehole images. So we are going to see some examples. So machine learning and CBT are useful tools that allow this a core study in an entire oil field using also these on-core wells. Phases and phases association can be predicted also using these multiple lithologic well logs. Usually when we perform electrophases analysis, we use just gamma ray or SP because people are very limited in trying to process at the same time different kind of logs. But this is not a problem for machine learning. And also we can predict the phases and phases association in all ways, and then we can integrate that in 3D seismic, so we can get more detailed subsurface mapping. Also we have to take care because every system is different and will require a detailed mapping to understand and predict new opportunities in undrilled areas. So this is some example of CBT. From CBT, the main power of CBT is you can process any kind of images in any format, and from these images you can extract and you can take any kind of information. that like morphologic information, textural information, component detection, and also you can measure different elements like, for example, bugs in carbonates. So different example of application of CBT. In this case, we use CBT to adjust the core in depth, calibrating the core with the images, borehole images. Then in this case, we get a detailed measurement of net to gross. For example, in heterolithic deposit, you can measure in detail. We can differentiate what is sandstone and shale and make a log showing that. You can measure the different size of the different pore. For example, in carbon, you want to map in the different logs where is the location of the areas in which bugs are more abundant or are bigger. Or you can make component detection. For example, if you want to recognize lamination, you want to recognize fractures, or you want to recognize any kind of element using these images. Then with the machine learning, we can predict the phases. For example, you can recognize different kind of elements according to CBT, and then you can propagate these elements using machine learning in other part in which you don't have the human supervision. So this is textural, the case of textural detection. You detect these elements, you map, and then you can predict. And also you can map different kind of rock types according to this recognition of different elements and different phases in the images or tomography. And then the software is going to create and to map the different rock types in all the wells. This is an example of an analysis of fluorescence using this UV photograph of the core, so you can get a definition of the historical boundary between, for example, water oil boundary. Another example, this is a more detailed example of element detection, for example, in which we apply in the recognition of fractures. You can measure the orientation, the size, extension, and all the dimension of these fractures, and we can create any kind of different logs. Or you can, for example, recognize different elements like a clast. You can measure individually the clast, and you can make a log that show all these characteristics. For example, this is the input data, this element detection, and then you have a log at the end in which you can differentiate lamination, fractures, and bugs, and create different logs to load into Petrel or any kind of software. So some example of CBT, morphologic log, texture logs. The more important point is we can customize this tool for the prediction or the recognition of any kind of element you have in your wells. So we can get the control of mapping what we want to map. So another example of how we can estimate the bug size in carbonates using these erosion dilation cycles. So this is a technology that was discovered many years ago and was applied to the analysis of thin section. We apply this in images, and also with using this CBT we can add some pixels and erode pixels, and after that we can get an idea of the size of the different kind of pores and the abundance of the different kind of pores. So as a summary, this is we can use, for example, using all these attributes, you can create a series of logs, and after that, using machine learning, we can characterize the different phases, and using multiple logs, we can create the last column is the prediction. Without human supervision, you can map any kind of phases also in other wells. For example, this last here is the prediction. This is mapping we make by a human. So the workflow, for example, is going from a core. Typical workflow is going from a core. Then this core, you create in the core you recognize phases association, and then we try to understand, to train these phases and phases association according to multiple lithologic logs, and finally we can make this, we can predict the phases along the whole well. For example, this is the here you have the core. This is the core here with the phases analysis, and then this core with training and machine learning, you can predict these phases also in areas in which we don't have cores, and we can apply this understanding to other wells that don't have cores. For example, this is a correlation that is supported by these phases. These phases were predicted using machine learning, and these are wells that only have well logs. So we can apply this correlation and make better correlation at the different scales. This is an example from Mexico of about the long-term correlation using a lot of wells. So it's very, because using machine learning you can process thousands of wells at the same time in a short span of time. So this is the workflow. From the core, you create sedimentological sheet, phases analysis, sedimentological analysis. Then when you apply machine learning and CBT, you can propagate this in the different well logs. Then you can integrate with seismic, and you can get a more consistent depositional or sedimentological model. So at the end, I would like to show some case study of deep water reservoirs we made during recent years, and so after this we are going to have some time for some questions and discussion. This was the previous model, is in a slope setting. So the main problem with this field, what this field, according to the seismic, people saw channels, some beautiful, they call these channels, meandering channels in deep water. The problem was that they put a well here in one channel, and they found that the channel was full of mud. So after that they said, okay, we cannot drill these channels because these channels are very risky. And the problem was they found a lot of sandstone on the levee, in the lateral part of these channels. And they found two channels at the same time, two coeval channels, because in the same time slice you can see a north channel here and a south channel here. So there was a lot of questions in these models. So our goal, our objective here was to try to understand why we have these two channels. The question is, are these channels in reality? And also, why channels are sometimes full of shale, and why you have this thick, massive sandstone also in interchannel areas? Because these are not Libby. These are different kind of deposits. So for this, we start with the analysis of near 300 meters, more than 250 meters of core. We describe those cores in detail. We perform phases analysis. We found a lot of extravaginal turbidites. In this case, phases analysis. We calibrate all this with logs, and after that, using multiple logs, we be able to predict these phases in all the wells you have in the area. So after that, when we put all these wells with the phases in the seismic, we can start to understand a little more. We made some Wheeler diagram to try to understand the time of working of the different elements. Here you can see in a time slice the two canyons here, the North Canyon and the South Canyon. And it's very interesting because, okay, here we have this the fast phases and also units, chronostratigraphic units, and you have these phases and the positional element. You have Libby deposit, you have sandstone deposit, you have mass transport complex, all these calibrated with the well logs. So we made a lot of different cross sections along the field, and this was fundamental to understand how this system works and what happened here with this growing structure. In fact, this was a diapir that grows up and controls the sedimentation. So for this reason, we could understand how the system works. At the beginning, we have just a canyon in the northern area of the basin, and this canyon, due to the growing of this diapir here, this canyon was blocked. This result in the accumulation of a transient fan here, with accumulation of sandstone and lobes. This sandstone infilled the canyon in this area, and on the other side, on this side, the canyon was abandoned. So it here was filled with mud, on this side was filled with sandstone. Then this canyon accumulate some more sandstone, and at the end you have mass transport complex and the second canyon that was elaborated toward the south. So this is step by step using Wheeler diagram and also the evolution. Of course, these canyons work in some moment, then you have periods in which discharge is low, then you have new activities, different activities of the canyon, and in the middle you have this shale accumulation. So very interesting, because in the Wheeler diagram here you can see, if you make a time slide at this position, you are going to see two canyons, because this canyon is very deep in sizing, and at the same time you are going to see the North Canyon. But these canyons are not coeval. The North Canyon is older, and at the beginning with this canyon, when this canyon was blocked, was initially filled with sand. Then you have the transient fan, different deposits, sandstone deposits along the canyon, and at the end, when you have an avulsion, you start to create a new canyon toward the south. So this red line shows the situation. This was the original situation here for the North Canyon, in which you have sediment bypass. Then, of course, this canyon was blocked, so you have the accumulation of sandstone here in transient fan. And then this transient fan becomes bigger, so you don't have any confinement here. And at the end, you have this shale accumulation in the middle that create a shale bed you can trace along different wells. Then you have the accumulation of a second transient fan, a short avulsion here. This avulsion is very interesting because it was blocked by a very thick mass transport complex, and at the end you have a new avulsion and a new incision in this lower part of the field. So it's very important to understand step by step, because here, as you can see, if you make an avulsion in this area, all the channel will be, all this canyon will be filled with mud. But if you make here, you block the channel, the canyon here, this part of the canyon will be filled with sand, and this part of the canyon will be filled with mud. So very important to map and to understand all the elements in a field. And okay, we can see here to explain better. So this is channel number 1, the older channel that was active until this diapir start to grow. When this diapir start to grow, we have here some block. You block the canyon, so this part of the canyon will be filled by mud. This part of the canyon will be filled by sand, sandy deposits, and also in different kind of transient fans here. That explain, this explain the amount of sandstone you have here. But at the end, you have avulsion here and a new canyon that develop in the southern area of the basin. So this canyon here is number 2. So not coeval canyons, but different canyons, and all these features create a very complex scenery for exploration. So in this cartoon you have here the original bypass to deep water. It's very interesting because nobody really worked here up to present, because all the exploration is in the slope setting. You have this growing here structure diapir here. So according to this growing diapir here, you have this transient fan here, and after the transient fan you have new avulsion and a new canyon that supply the sediment to the inner part of the basin. So the main difference of the two different models, this was the previous models in which you have a channel Libby, and here we have a channel fill and spill and transient fans. This model was based on seismic, this is based on core. You have Libby and small channel fills. You have ponded canyons and lobes. The canyons or channels in the previous model are synchronic. In our model, these canyons are diachronic. The migration is gradual. The migration is episodic in this model due to the avulsion. The infill with mud, the canyon, and very important, In this model, you can predict where the canyon is filled with sand and where it's filled with mud, so you can decrease drastically the risk. And also, the prediction of new opportunity is very important if you take control on your depositional environment and your depositional setting. So going to some conclusion. Okay, intrabasinal and extrabasinal turbidites are very important for the transfer of huge voluminous sediments into shelfer and inner basin areas. One, intrabasinal turbidite, because gravity collapse of part of the slope, or the transfer from rivers in flat for the case of extrabasinal turbidites. Intrabasinal turbidites are efficient mechanisms to restore the equilibrium profile on sedimentary basin in which you have shelfal and slope settings. But the triggering of this intrabasinal turbidite are mostly related to this gravity instability, sometimes can be induced by tectonic activity or collapse of sediments accumulated close to the shell margin. As you know, many models relate these intrabasinal turbidites to low stands. But in contrast, extrabasinal turbidite can happen also during high stand. You know, the excellent example of Eocene turbidite you have worldwide. The Eocene was one of the periods in which the sea level was at the maximum because it wasn't hyperthermal, no ice during the Eocene. But many turbidites are Eocene in age. So extrabasinal turbidite allows the direct transfer from the continent of freshwater sediment and organic matter, mainly plant remains, to the shelf and also to inner basin areas. The volume of plant remains can be very important. In some situations can be also source rock for oil and gas. And depending on the volume of the fluvial discharge and the grain size of this turbulent suspension and bedload, the deposits can be very different and can compose beds of sandstone and conglomerates with multiple grading, composite beds, and also a lot of plant material and plant remains. Very important, the final thickness and extension of the deposit will depend on the duration of the fluvial discharge and the basin topography. This is very important for the definition of new opportunities in deep water and ultra deep. And the origin of extrabasinal turbidite is mostly related to climate. So is partially independent respect to the position of the sea level. Not all extrabasinal turbidites are related to low stand. You can have also a lot of extrabasinal turbidite during the high stand. And from our point of view, extrabasinal turbidites are deep water deltas, and the deposits can extend very far from the slope. And very important, every system is unique and should be studied in detail. So the fan slow model, very popular in the textbooks, are very risky because you cannot understand extrabasinal turbidite with the models of intrabasinal turbidite. So sometimes perhaps one of the problem is the size of the deltas. Deltas can be very big, can be a huge animal. This is some example of, if we compare the size of littoral deltas on the Bengal fan, for example, or this is the Indus fan, and you see the size. For example, this is the slope, the location of the slope. As you can see, the main accumulation in this Bengal fan is not at the end of the slope. You can find deposits very far from the littoral delta. In this case, near 4,000 kilometers from the littoral delta. And if you drill a well here, you will find a lot of plant remains, many papers showing that kind of situation. So it was our pleasure to be with you today and to share some concepts. This is our amazing outcrops from Ushuaia in the southern part of Argentina. A lot of excavation and turbidite with very interesting faces. You can walk from the shelf to across the slope to the inner basin areas. Very amazing outcrops, amazing examples to try to understand better deep water deposits. So thank you very much for your attention. It was our pleasure. We are open for questions.